Hi everyone, I'm Jai Mardia. I'm a graduate student at Stanford University, and today I'm going to talk with you about the following question, which is the space complexity of planted clique recovery the same as that of detection? Now, there might be words out there that in there that are unfamiliar to some of you. Don't worry about it. We'll get there together. But before we get there, we need to look at a slightly different question first. And this question is, what is a tractable inference problem? If you ask a statistician this, the statistician will say to you, well, if you can extract some sort of signal from the input, despite the random noise that might be present, then it's tractable. Okay, that's great. If you ask the same question to a computer scientist, you might hear, well, if there's an efficient algorithm to solve the problem, then it is tractable. Okay, so you have two different notions of tractability, and we're not sure whether they coincide or not. Be great if they do. However, this sort of problem has been studied a lot in the past few decades, and the consensus that has built up is that these two notions do not coincide. In fact, for several problems like planted clique, sparse PCA, tensor PCA, uh, people have come up with ways of predicting and understanding when uh, computationally efficient algorithms exist. And it turns out that there is a gap between where statistics says things work and where computer scientists say things work. So far, I've given you a fairly abstract uh, view of this sort of misalignment between these two notions. So let's look at a concrete example to make things clearer. Let's look at the planted leak problem. And this problem is basically one where there's a planted leak graph. What is this? There's a random graph on n vertices, and there's a subset of vertices of size k, which is picked uniformly at random. And a clique is added on to that subset of vertices. I don't need you to remember the details of this problem too much. All I need you to understand is that there are n vertices. There is parameter k, which ranges from 1 to n, which you want to think of as a signal to noise parameter, signal to noise ratio. And uh, there are two variants of this problem. The first is called detection. In this variant, you're either given a completely random graph or you're given a planted clique graph. You don't know which one, and you have to figure out which one. You want to detect whether or not a clique has been planted in the graph that you've been given. The second variant, which is formally at least as hard as the first one, is the recovery variant, where you've been given a planted clique graph and you need to find the subset of vertices on which a clique has been planted. Okay, that's good. Uh, it may not be obvious, but it is true that as k increases, the problem becomes easier. In fact, a statistician would tell you that if k is larger than 2 log n, then this problem is solvable. No problem, no issues. Detection, recovery, both of them, we can do it. Computer scientists started asking, well, okay, but are there efficient algorithms to do this? Uh, it turns out that for the algorithm that sort of works above the statistical threshold of 2 log n is not efficient. And all the many polynomial time algorithms that have been uh, sort of designed for this problem all fail to solve it below k equals square root n. K is order of square root n. In fact, people have gone further and studied uh, classes of algorithms and like convex hierarchies, statistical query algorithms, algorithms based on low degree polynomials, and shown that provably all of these fail to give polynomial time algorithms for k smaller than this threshold. And what this has done, it has cemented the belief that there is an exponential gap between the clique sizes or the signal to noise ratio at which statistics says something is tractable versus where uh, computational efficiency considerations say something is tractable. Okay, that's great. I've given you one concrete example of a problem where such a gap exists, and I've also told you that this sort of gap exists in many other problems. But one thing I've kind of swept under the rug is that I didn't formally tell you what we mean by computational efficiency. And perhaps you've already understood that what we meant here is a computationally efficient algorithm is one that runs in polynomial time. And to you, this might be an extremely reasonable thing to do. We have decades of experience with equating efficiency with polynomial time algorithms. And even more important, making this identification here has led to a very nice understanding of statistical computational gaps, or this misalignment between these two notions, so much so that we even now have a bunch of reduction based evidence for hardness of different problems in this sort of vein. Now, having said that, computer scientists do indeed study other notions of efficiency. They study things like space complexity, or streaming complexity, or communication complexity. These are all useful in different contexts, but even more importantly, they seem to have insights into situations where we would not have expected them to have insights. Space complexity turns out to be useful in understanding the complexity of two-player games. Communication complexity turns out to have uh, a tremendous amount of use in understanding the streaming of complexity of problems. So what this suggests is that even in the statistical context of uh, statistical problems, it might be useful to consider notions of efficiency other than simply polynomial time algorithms. More importantly, one could argue that the study of statistical computational gaps already implicitly does this. On the previous slide, I gave you a bunch of restricted algorithmic classes that people study and get provable guarantees for, saying that no polynomial time algorithm within this framework can sort of solve the problem below a certain threshold. One could say that what they're doing is studying a non-standard notion of resource or complexity. For example, it could be the number of levels in a convex hierarchy, or it could be the degree of a polynomial that we use to compute with. And a lot of the success in this field has come from studying these non-standard notions of complexity, although this is only implicit because the lens with which people view these results remains firmly that of equating efficiency with polynomial time algorithms. What this suggests is that maybe we should explicitly study alternate notions of efficiency in the statistical context, and maybe that might turn out to be interesting. Okay, so suppose we agree that we should study alternate notions of efficiency in this context. What is the first thing we should do? One could argue that the nicest thing about uh, this study of statistical computational gaps has been the very fact that we can find that they exist. We can find their locations, and it would be kind of sad if we change the notion of efficiency we use and suddenly these gaps disappeared, or maybe more quantitatively speaking, the locations at which these gaps appear changed too much. Kind of what we're asking is, are these gaps fundamental to the problem, or do they depend very heavily on the notion of computational efficiency we use? Okay, so this slide is kind of the stepping stone for the work we're going to discuss today. These questions are very broad and understandably hard to answer. What the work we're going to discuss does is it takes one step towards trying to answer these problems by looking at one specific problem and one specific notion of complexity and trying to see what happens when we put them together. By an by a stroke of luck, I have already introduced the problem we're going to discuss, the Planter-Clique problem, so I don't have to do it again. What we really care about now is trying to study whether um, the space complexity of the Planter-Clique problem throws up the same sort of statistical computational phenomena as the polynomial time complexity. What were these phenomena? Well, first we saw that a statistical computational gap existed. Second, while we didn't see this, what is true is that this problem turns out to have a central place in the sort of web of reductions that people use to reason about equivalences between different statistical problems. And third, uh, which I didn't stress, but it turns out that there is a formal reduction between these two problems, which makes the time complexity of detection and recovery basically the same, at least if we look at it in a coarse grained way, by saying that the time complexity is the same if it is uh, within a polynomial factor of each other. And ideally, we want to say that if we study the space complexity of the problem, these phenomena also happen. We won't look at two, that's a bit too ambitious for this work. But what we will look at is points 1 and 3 and hope that we can show that these sorts of things also happen for space complexity. Okay, so what is space complexity and what is an efficient algorithm? Well, space complexity is basically just trying to measure how much memory or working space you require to solve a problem. Think of it like how much scratch paper you need to solve a complicated math problem. Uh, this is a very well studied notion of complexity, and it, it has emerged that the correct notion of efficient space bounded algorithms is that of logarithmic space algorithms. So you have logarithmically many bits in the size of the input, and that lets you do a lot of nice things. So this is the sort of benchmark we're going to use to understand what an efficient algorithm is in this world. Another reason to do this is that if an algorithm works in logarithmic space, it also works in at most polynomial time. This means that the Planté-Clique conjecture, which is a conjecture that there are no polynomial time algorithms below the square root n threshold for Planté-Cliques, immediately sort of would imply that there are no log space algorithms for these small cliques either. Okay, what are some easy to see facts about the space complexity of the Planté-Clique problem? Well, it's actually quite easy to see that just above the statistical threshold, we can use already existing algorithms that work in quasi-polynomial time uh, and just analyze their space complexity. And it turns out they require log square n bits of space. That's not efficient. So but it is the best we seem to be able to do right now. And if the Planté-Clique conjecture is true, we also don't expect that the complexity out there to go down to logarithmic number of bits. For the detection version of the problem, as soon as we're above the root n threshold, we can actually solve this problem in logarithmic space very easily. This is because just counting the number of edges in your graph gives a good is a good test for whether the graph has a planted clique of that size or not. And counting the number of edges is something we can easily do in log space. Okay, but this doesn't say anything about the recovery problem for large K, because the number of edges is not it's not going to help us recover the planted clique. It just tells us that one exists. And so this is where the question now becomes, is the space complexity of planted clique recovery the same as that of detection? Uh, some of you might notice that this was also the title of the talk. And why is this important? Well, if we can show that such an algorithm exists, then the time complexity based statcomp gap would also imply a space complexity based gap, because the time complexity based gap would imply there are no polynomial time algorithms and hence no logarithmic space algorithms below the root n threshold, while above the root n threshold, uh, we would have found algorithm for a log space algorithm for recovery. This is already true for detection, but not necessarily true for recovery as far as we know so far. The second thing this will show is that the coarse-grained complexity of detection and recovery are the same, no matter what notion of efficiency we use, space or time. I won't go into details of what exactly we mean by coarse-grained, but you can look at the paper. And what this would do is that it would show that this threshold signal to noise ratio or clique size of square root n is essentially something fundamental about this problem. It's robust to changes in the notion of efficiency. It's robust to changes in the formulation of the problem, whether we're looking at detection or recovery. And that is why we want to show that a log space algorithm for planted clique recovery exists for k above the square root n threshold. Okay, how might we go about doing this? Well, maybe previous polynomial time algorithms can be adapted, or maybe if we analyze their space complexity, maybe we can implement them efficiently. So let's just take a look at what the previous literature says. One thing I've already mentioned to you is that there is a formal reduction between detection and recovery uh, from Alon et al. In 2007. What they do is they give, and if there is an algorithm to solve the detection problem, they give an algorithm to solve the recovery problem. If we can implement this reduction space efficiently, then we should be done. In fact, we can implement this reduction space efficiently, but unfortunately, we're not quite done. The catch is that the statistical success of this reduction depends on the failure probability of the detection algorithm being quite small, little o of 1 over n. And unfortunately, the log space detection algorithm that we have does not have a failure probability that small. And so this reduction idea does not quite work. Okay, why don't we actually look at the polynomial time algorithms that exist and see if they can be implemented efficiently? Well, a spectral algorithm by Alon, Krivelovich, and Sudokov was the first polynomial time algorithm that could solve the planted clique problem, the recovery problem for cliques above size root n. What we need to do to use this algorithm is to compute an eigenvector of the adjacency matrix of the graph. This eigenvector obviously requires polynomial in n number of bits to specify. So it's not clear how to implement this space efficiently or to compress this eigenvector. Having said that, there could be hope for a spectral algorithm. The eigenvalue corresponding to that eigenvector serves as a detection test for planted cliques. And more importantly, it's the failure probability of the test that uses the eigenvalue is much smaller than little o of 1. So if we can compute that eigenvalue and use the reduction from Alon et al., then we'd be done. Unfortunately, we do not know how to compute that eigenvalue to the desired accuracy in logarithmic space. Okay, what next? Well, there are a bunch of optimization theoretic semi-definite programs that solve the planetary recovery problem. Can we implement any of those space efficiently? Well, unlikely. Uh, at the very least, we know that there are no generic log space algorithms to solve semi-definite programs. If we did, then it turns out that every problem with a polynomial time algorithm would have a log space algorithm, and we do not believe this to be true. Okay, maybe let's look at the class of combinatorial linear time algorithms that have been developed in the past decade or two. There's an algorithm by Feiger and Ron which maintains a vertex subset and decreases it by one in every round, by one vertex in every round. And it sort of removes vertices that it thinks are not in the planted clique and eventually ends up with essentially what is the planted clique. Unfortunately, for most of its runtime, this algorithm has to maintain a polynomially large subset of the vertices, which we can't do in log space. And there does not seem to be any realistic way of compressing this set so that we can uh, implement it space efficiently. The algorithm of Deshpande and Montanari sort of is a message passing algorithm, and it produces a dense n cross n matrix in every iteration. Clearly, we can't do this in log space, but there might be a space efficient implementation of this message passing algorithm that sort of recomputes messages when needed. Unfortunately, this algorithm requires logarithmically many iterations or recursions, and each of these sort of rounds would require logarithmically many bits, and this would bring us back to a log square n space algorithm, which we kind of already know exists just above the statistical threshold. Finally, there's an algorithm by Deckel, Gurel, Gurevich, and Perez from 2014 that also does something like the 5-Piron algorithm, where it maintains a set of vertices and improves the ratio of clique to non-clique vertices in every round. Unfortunately, this algorithm uses randomness and uh, also depends on the edge structure of the input a lot. And so, again, it's not really clear how to implement this space efficiently. It seems like we might need some new ideas to do something here. Having said that, one of the new ideas will be trying to see how to de-randomize the DGP14 algorithm, although we won't get into the technical details today. And so I'll just tell you about what our main result is. The main result is that we come very close to our desired goal, but not quite exactly where we want to be. We can uh, you can create a recovery algorithm that solves the problem for k larger than root n in this ugly looking space complexity bound. Um, the log star function is simply the number of times you need to the height of the power tower you require to reach n. So, for example, the log star of 2 to the 2 to the 2 to the 2 would be 3, or was it 4? Anyway, you get the idea. It's very, very, very small. Uh, let's look at two cases to understand it better. Suppose k is little omega square root n times log ln, where if L is, say, 3, then it's square root n log 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 n. And basically, L could be any constant integer. And the space complexity of this algorithm that we design would be O of log n. That's good. If k is theta of root n, though, the space usage would actually be log star n times log n bits. And so what this is showing is that while we come very close to the desired space complexity bound, we don't actually reach there. However, this does suggest that the desired log space algorithm exists. And this suggests that the statistical computational phenomena that hold for time complexity also hold for the space complexity of this problem. I'll end by mentioning a couple of open problems. The first is the obvious open problem, which is there a log space algorithm uh, that recovers planted cliques of size omega of root n? And the second, more vague and open-ended open problem is there a more generic way to study these gaps for large classes of problems? Here we've taken one problem, one alternate notion of complexity, studied it, but it might get annoying to have to do this for all the problems for which we have statistical computational gaps. So is there a more generic way of trying to do this? And that is the uh, end of my time here. Thanks for listening, and thank you.